Now let's see next example 4. Find the equivalent resistance at the terminal A and B in the circuits A through C. So this is pretty much looking for the total resistance. How to solve such kind of a problem? Remember two things. Number one, there are only 4 types of connections you need to identify. And they are series, parallel, delta, or Y. Okay, only 4 you need to identify successfully as the basis of finding the equivalent total resistance. Second thing you need to do is following the circuit order. Begin with the end of the circuit and moving towards the beginning of it, part by part. Okay, following these two ideas, let's try circuit A here. Okay. We're beginning from the end of circuit. Actually, we're considering the terminal A and B as the beginning of the circuit. So the end of it is pretty much this part, from where we can see a clear series connection between 3K and 6K. Combining these two, and then we see a clear parallel between 18K and this combined 3 and 6K. After that, we see this entire thing is series connected with 6 and 10K. And then pretty much we are done with finding the total resistance RAB. And here is the solution here. 3, 6 series parallel with 18K. Well, of course, here I've been using this parallel double bars as the representation of parallel. Let me know if you don't follow the meaning of it. Okay, so parallel will follow the parallel equation. You can calculate 1 over the sum of reciprocal of each one. Okay, and then series with 6K and 10K. The correct result is 22 kilo. And to go back to the circuit B here, again, we follow the order of from the end of the circuit, beginning of the circuit, and the end of circuit is obviously here. Another clear series connection between 1K and 2K. After this, you can see a clear parallel between this 6K and this 1K, 2K. After combining these two parts, you see another series with 10K. And so on and so forth, move towards the beginning of the circuit. And at last step, you can imagine that actually series with this 2K up here. Right? So try yourself to see if you can get the correct result. The last circuit C here, you're seeing something different. You're seeing a delta connection, right, among these 3. Or you're seeing another delta connection among these 3. They're overlapping by this 18 kilo ohm, therefore you don't need to do 2 conversion from delta to Y. You want to do only 1 conversion from delta to Y, either upper one here or lower one here. Only 1. The goal of converting delta to Y is that the result could have clear series or parallel. Since now, without doing that conversion, you can't see any clear series connection nor parallel connection. Okay, so be careful. All right, so try yourself and then come back for the solution. And here you're seeing the solution for B, bunch of series and parallel. Okay, so let me know if you have any questions or any part I need to teach more. And to circuit C, I'm converting the upper delta to Y following the conversion equation provided in the previous slide. So after that, I end up with 3 resistors here. So from here, you can see clear series connection between this one and this one. Also, between this one and this one. After combining them respectively, you see these two are actually parallel. And then from there, you basically know what to do to the next. Okay. The correct answer for this total resistance is 34 kilo. Right, next example, number 5. Well, you can notice that the difficulty level is actually increased gradually. And let's see, find different things in different circuits. First, circuit A, looking for the I0, which is the current through 3K here. Okay. How to find it? First of all, remember there's always more than one ways to solve the same circuit. And here, based on what we have just learned, I'm planning to use the current divider. The reason is I'm seeing one independent current source here, which is pretty much providing the total current to the entire circuit, or say network. So if I can somehow combining the rest of circuit into 2 parallel branches between the single pair node, I can apply the current divider to find the current anywhere. So based on this thought, I start to work towards that way. So I'm seeing, first of all, 3K and the 6K here are clearly parallel connected. So if I combine them together and then series with 4K up here, it becomes one single branch, which is parallel with this 12K branch. So clearly a basic current divider. Of course, you're seeing 2 elements. By that, I'm saying pretty much one branch parallel with another branch. Only 2 branches, 2 elements, share the total 9 milliampere current. So by doing this, I'm able to find this branch current, because the ultimate goal is to find the I0 here. So find the current through 12K is meaningless. So find this branch current, which is also the current through 4K. This is a very important thing you need to realize. So the current flow through 4K is in which direction is another thing you need to figure out. So if you think of this circuit, so basically 4K current and 12K current total is equal to 9 milliampere going downwards. So from here, the current of this 9 milliampere is towards right. Therefore, the current of 4K is upward, the current of 12K is towards right as well. Does it make sense? So the sum of these 2 current equals to this current. And this is how I judge the current direction of 4K. Due to that, you can see the 4K current is actually the sum of the current through 3K and 6K, which is the second current divider here. And the 3K current, for the same reason, is upward. So is the current direction of 6K. So by applying the second current divider, you can find I0. This is pretty much I0. However, it has the opposite current direction compared to the given one, label one, which is downward. So what we need to do is this current is actually not I0, but negative I0. Right? So by 2 current divider and a little combination, you can do the job. So here is the solution specifically. So first of all, as I said, looking for the current through 4K. We know the current through 4K is supposed to be upward. However, if you're looking for the downward current, is actually equals to negative total current times the ratio. In the numerator is the other branch resistance, which is 12K. Denominator is the sum of 12K and the 4K branch containing the parallel between 3K and 6K here. So the current through 4K downwards is -6 milliampere. And using this current to do second current divider shared by 6K and 3K, since they're in parallel, you got I naught, -4 milliampere. Now let's see circuit B here. So based on circuit 1 analysis, we should be able to open our mind to an idea that as long as we are seeing only one independent source, we might want to think of voltage or current divider as one of the solutions, at least. Here, be careful. It must be one independent source. No more than that. If you have two independent sources or even more, no, you can't do that directly. If you have one independent source and you have one or more dependent sources, you can't do that either. Okay? It must be one single independent source, and then you might think of current or voltage dividers. Okay, so this is also the case for circuit B here. Also C and D. So pretty much example 5 is all about the voltage or current divider. Okay, so going back to circuit B here, one independent voltage source. So we are thinking of voltage divider. So how to do that? Again, no matter is current or voltage divider, we need to think of two elements. Okay, total voltage here shared by two elements. If there are more than two elements in the circuits, you need to combine them, becoming two, and then you apply the voltage divider equation. Okay, that's a very, very important thing. So to do that, obviously, we can clearly see a series connection between these two. After that, this guy is parallel with 30. Okay? And then this total thing gonna share the 12 volts as total with this 20 kilo ohm. Okay? So pretty much this guy is series connected with this guy in the single loop circuits, so that we are able to apply voltage divider between these two. Okay. After that, you got the voltage. That voltage is the voltage cross here and here, right? Which is not equal to V naught, the one we are looking for. Okay, be very careful. And clearly, you're seeing second voltage divider. The total voltage here is shared between 20 kilo and 40 kilo here. So by this second voltage divider, you should be able to find the voltage across 20 kilo ohm, which is our true V naught as the final result. If all of this saying makes sense, please take a look at the solution here, from where you can see two voltage dividers. Total 12 shared by 20K, and the combination of those three. And you're looking for the combination voltage, which is also the voltage across 30 kilo. And by applying the second voltage divider, as we said, you're looking for the voltage across the 20K as the final result V naught. So the correct final result is 2 volts V naught. Similarly in circuit C here, clearly one independent voltage source. We are thinking of voltage divider again. This is actually easier than circuit B. However, the trick is it is looking for the VS, which is the total voltage. How could we do that? We can find the voltage cross 60K, which is the voltage here, from here to here, between these two nodes. So pretty much if you combine 60K and the 120K, you can see their combination is series with this 20K here, becoming a single loop circuit here for you to write voltage divider equation. And then the voltage here could be found by that, and it equals to the voltage cross 60K. And 60K voltage is equals to the current times resistance based on the Ohm's law. So following this idea, so 6K ohm voltage is equals to resistance times the current equals to 6 volts. And by applying voltage divider, it is also equals to total voltage times a ratio. And the numerator is the combination between 60 and 120. Denominator is sum of 20 and this combo. Is equals to the 6 volts we obtained here, from which we can find VS value. So the correct answer is 9 volts for VS. The last one, single independent current source. So we are thinking of current divider. And we again need to combine the rest of the circuit into two parallel elements, branches, to share this total IS. So similar to circuit C idea, we don't know the total current IS. However, we can find one branch current, which is here. So this current following this given voltage with its polarity is going downwards current 3 volts divided by 30 kilo ohm. After knowing this current, we can combine 90 kilo ohm and 30 kilo ohm together. Becomes one branch parallel with another one. So two branches, two elements share the total IS as this. So the 30 kilo ohm resistance current is equals to the voltage divided by resistance, 0.1 milliampere. Be careful, it's downwards. And then by one current divider here, we can find this current is also equals to total current times the ratio. In the numerator is the other branch, which is 6K. Denominator is sum of 60K and this branch, which is series connection between 90 and 30K. Equals to 0.1 milliampere, which we obtained from up here. From this equation, we can find IS equals to 0.3 milliampere. But here, pay enough attention on this current direction. We call it downwards. The reason is going back to the circuit, because the positive is here, negative is here. So you use this voltage divided by 30 kilo ohm, give you the current from the positive higher potential point towards the lower potential point, negative. Actually, same attention should be paid in circuit C, in where the given current 0.1 milliampere through 60K ohm is downwards current, introducing the voltage having the voltage polarity positive up here, negative down here. So imagine, what if the current direction given is another way around, upward? How to solve this problem? So now we finished all of the content of Module 1, including basic concepts, connections, relations, and followed by several examples. Please review the knowledge and especially spend enough time on practicing the examples yourself. Bring up all of your questions in office hour. Fully utilize it. Thank you. See you in next module.